and then share screen, and we're good to go. Okay. So today we're going to talk about normalization. This is related to functional dependencies, the topic we discussed on Tuesday. So we talked about what are we trying to do right now? We're trying to assess how well a database is designed. So you've already had a database that is materialized in a database management system, and you want to assess how well it's designed. If it's poorly designed, you want to fix this. And the issues that come up are basically redundancy. So you have repeated information. So information that should not be repeated, that is repeated in your database. And these cause update, insert, and delete anomalies. So basically this redundant information if you're updating one of them, you have to update it everywhere. Otherwise your data is inconsistent. You cannot insert certain things because of functional dependencies. And if you delete certain things, you might lose information that you wanted to keep in your database. So normalization is the process of decomposing a relation, a table. You take it and decompose it into multiple tables to eliminate the above issues. Yeah. So here's an example relation. This is the one we looked at last lecture to motivate this issue of redundancy. So here we have major and minimum credit, and major is functionally determines minimum credit. So you have basically based on for whatever value of the major, you have the corresponding value of minimum credit. So CS is 90, math is 120, and English is 80. Yeah. So this functional dependency is causing all these issues with redundancy because you're repeating the minimum credit with every student. Yeah, that is in the major. Okay, the right way to do it is to break it down into two relations or two tables, student and major, where you store the minimum credit of every major only once. Yeah, so this is what is called normalizing the table into a normal form. So what are these normal forms? It means the following: a relational database whose relations are all in normal form is a well-designed database. It means that it doesn't suffer from redundancy and anomalies. That's our goal. We want to make sure that your database, whatever database you're creating, is in normal form. The two most important and common normal forms are bias cod normal form, so BC and F, and third normal form. Yeah, there are also second normal form and first normal form, but typically if you're using the relational model, then everything is in 1 NF and 2 NF. Yeah, so the issues usually come from that the data is not in 3 NF or BC NF. So we're going to understand each one, what does it mean, and how do I make sure that my database is in one of these normal forms. Now, as I said, this could come up because you're just joining the database team and you have already an established database. Typically, if you're using the ER model and all the guidelines that we've been telling you, you have very high chance that your data is going to be in a normal form. But you need to ensure this. As you're creating your database, you need to ensure this. So I recommend that for your project, you also make sure that your data is in one of these normal forms. Yeah, so that, and if it's not, you normalize it. Yeah, so if you made a poor decision in design, then you need to fix it by making sure the data is in normal form. Okay, we'll start with bias cod normal form. So relation R is in BC and F, if and only if. So for any non-trivial functional dependency, alpha determines beta. You have alpha as a super key. Yeah, so you have to look at all the functional dependencies that exist in your table for every table that you have in the database and make sure that the left-hand side is a super key. Again, what is a super key? It means it's unique, or it means that it functionally determines every attribute in the relation R. Okay, let's look at an example. So let's assume I have the student table, which has these attributes, and its primary key is ID. And I know I can tell from the data. So if I don't have these functional dependencies, I can deduce them from the data, yeah, by looking at the values inside every attribute. So after I do this, I get the following functional dependencies. That ID determines every attribute in the table. So it determines ID, name, email, major, minimum credit, and GPA. And also major determines minimum credit. Yeah? So I can deduce these two sets of functional dependencies. Okay, so it's the question now is student in BCNF. What is BCNF again? It means that, you know, for every functional dependency that I have, whatever is on the left-hand side is a super key. Okay, so let's check. The first one, or the first set of functional dependencies, yes, ID is a super key because it's the primary key, so of course it's a super key, hence it's unique, hence, right, it determines all the attributes in the table. And so this first one, or first set of functional dependencies, ID determines ID, name, email, etc., does not violate the BCNF condition because ID is a super key. Now let's look at major determines minimum credit. Is major a super key? The answer is no, right? The answer is no because major is not unique. It's not a unique column. So major determines minimum credit is a violation of the BCNF. Okay? Any questions? You understand what I'm doing? Okay, good. So this is the algorithm to decompose a relation that is not in BCNF into BCNF. So given a relation R and a set of functional dependencies F, you look in F for a BCNF violation. So for example, X determines B, where X is not a primary, a super key, okay? What do? You compute the closure of X, and we talked about what is the closure of X. It's all the attributes that functionally depend on X. Yeah, I would repeat this to remind you of it in a given example in a bit. Okay, so I compute X plus the closure of X using the functional dependencies F, and then replace R by two relations as follows. First one is the closure of X, so basically all the attributes that depend on X and X, and the second one is just all the other attributes and X. I'll explain this using an example in a second, right? Then you do what? You project your F into R1 and R2, so you take all the functional dependencies. Now you have two new tables. So you have to, you know, map these functional dependencies, or the original functional dependencies which were on the original table R, into these two new tables, R1 and R2. You get a new two sets of functional dependencies. And then you again make sure that they are in BCNF, and if they're not, you recursively normalize again. Yeah. So this is what you do. Now, just one quick remark, and then we move on to an example. You have to make sure that your whole database is in BCNF, meaning what? That every table is in BCNF. Yeah, and every table is associated with a set of functional dependencies, and so you can verify this using the set F corresponding to R. This is how it graphically looks like. Yeah, so you have R was this whole table. You have X is one attribute, right? That is left-hand side of functional dependency. You break it down into two relations. The first one is the gray one, right? And the second one is the yellow one. The gray one is basically everything in R minus the closure of X plus the column X, yeah, or the set of attributes X. And then the second part, the yellow, is the set of attributes X and the closure minus X. Yeah, so the attributes that depend on X. Okay, before we go into the algorithm and do an example, just a quick remark on projection. What does it mean to project a set of functional dependencies on a new relation? You basically you compute the closure of X, right? So you get X plus, and then return all non-trivial functional dependencies that involve attributes in R dash. Let's see an example. Let's start with projection. Yeah. So let's start because this is used in the main algorithm of BCNF. So let's do the following. Let's say I have the following relation A, B, C, and I have two functional dependencies. A determines B, and B determines C. Meaning what? Meaning that the value of A decides the value of B, and the value of B decides the value of C. We want to compute the projection of F on R dash equal A, C. So how do I do this? I do the following. I compute the closure of A. So basically, I'm going to do it here on the slide. So I compute the closure of A because I have A determines B. So I'm going to compute first the closure of A. First of all, these two functional dependencies, I cannot use them on R dash, right? So basically, because they involve an attribute called B, which is not an R dash. Yeah? So I have another table R dash, which has two columns A and C. So neither of these functional dependencies are relevant for R dash, right? But there are other functional dependencies that I could deduce from these, of course, A determines B and B determines C, that are relevant for R dash, that involve attributes in A and C. The easiest way to do it, of course, I can use, transitivity and get that A determines C, but the systematic way of doing it is to compute the closure and then move on. Okay, so I have the closure of A is what? A and B. And since B determines C, I get also C. Okay, good. So what are the functional dependencies I can, infer from A, from this closure? I can infer that A determines B. Non-trivial ones. Yeah, so A determines B, and also A determines C. Okay. Let's compute, the functional dependency of B. The closure of B, I mean. It's B and C. Only B and C. And so from this, I deduce that A determines B, determines C. Okay. We need to do this also for pairs of attributes, but let's focus on this alone for now. So what is the functional dependency out of all these functional dependencies? What is the functional dependency that is relevant for R dash? It's this one, A determines C. So this one is the projection of these two functional dependencies on A, C. Of course, I could have used also transitivity and got that A determines C is this, okay? So here is what I did. I computed right? So I also need to do this for basically all subsets of attributes in R. So not only A and B, I need to do it for also C and for AB, right? So for C, we have only no non-trivial functional dependencies. For AB, so I need to do it for all subsets of the relation R. So if it has 3 attributes, then you'd have, all possible subsets of these. So A, B plus is A and B determines C, so I get C as well. So that's one functional dependency, A, B determines C. I have AC plus, that's A, B determines C. I get from that AC determines B. And then for BC plus, I get B and C, so there's no non-trivial functional dependencies. Okay. And then for output, the functional dependencies are only relevant to R dash. So I have the following set of functional dependencies. A determines B, A determines C. So this is relevant to A and C. So I will highlight it. B determines C is not relevant to A and C. This one is not relevant to A and C because it involves the attribute B. This one also involves the attribute B, so it's not included. And this one doesn't have any non-trivial functional dependencies. Okay, so you get from all of this, that A determines C is the only, relevant functional dependency that could deduce from the original table once projected on R dash. Okay, questions? Okay, let's do another exercise on this. We're gonna do some shortcuts, so we don't have to do this for every possible subset of attributes. So if I have 4 attributes, this would be too long. We're gonna do it only for, basically what you need to do is when you're projecting F on R dash, which contains, other attributes, or a smaller set of attributes, sufficient to consider subsets of R dash only. So only things that involve, right, the new table. Anything that involves any other attribute would not be relevant anyway. So here I should consider only A, and then C and D, and then AC, AD, and CD. I don't need to consider things that involve B at all, because they will not be relevant anyway. Second thing is, if I have an attribute or a set of attributes that basically determines all other attributes of R dash, then I don't need to consider any superset of X. So let's do this exercise and that will become clear. So what do I need to consider? I need to consider A, the closure of A, first single attribute. So what is the closure of A under F? It's A, B, and then C and D. So all the attributes in A, in R. So it's A is the key of R. Okay. So from this, I can deduce the following functional dependencies: A determine B, which is not relevant because the R dash doesn't have B. A determines C, and A determines D. Okay. Can compute. Now I'll skip B because B is not part of R dash. So it's all of the functional dependencies that I will deduce from the closure of B is not relevant. So then I'll go to C directly. C is the closure of C is C and D. So from this, I get the functional dependency C determines D. And then I'll compute the closure of D. It's just, there's no functional dependency with D at the left-hand side. Okay. Now I should also compute basically AC, the closure of AC, the closure of CD, and the closure of AD, and the closure of CD. So let's do it, since we don't have any basically attribute that determines, except for A. So basically, I don't have to consider AC and AD, right? Because the closure of A contains all the attributes in R dash. So I don't have to consider AC. I don't have to consider AD as well. Why? Because A determines all attributes in R dash, and hence, right, any superset of it is not needed. But I need to do CD. So the closure of CD is just the attributes C and D. Hence, there are no non-trivial functional dependencies there. So I get from this that the only relevant, functional dependencies that I can project are A determines C, A determines D, and C determines D. Right? So the functional dependencies from F that are relevant is A determines C, A determines D, and C determines D. Note that, right? You didn't have A determines D before in the original set F, and you didn't have A determines C, right? You deduce them by doing the projection, by doing the closure. Questions so far? Now everything is clear? Okay, good. So yes. Okay, good. So now let's go back to BCNF. Again, remember what is BCNF? BCNF means that a relation, there's no functional dependencies for which the left-hand side is not a superkey. So every functional dependency that I have has on the left-hand side a superkey. If we go back to our table, student, we had major determines minimum credit. This is a violation of BCNF. Violation of BCNF. Why? Because the answer is major is not a superkey. Super. Okay. So basically, major is not a super key, hence this is a violation of BCNF. So how do I decompose it into a set of relations in BCNF? I take major, compute its closure, and contain a table, create a new table which has major and all the attributes that depends on it. So basically, all the attributes that are in the closure of major. And then the other table would be all the other attributes plus the attribute major. So let's do this. What is the major, the closure of major? It's just the two attributes major, right? And minimum credit. Minimum credit. Yeah, I'll shorten minimum credit into this. Okay, so then I have one table which has major. So I'll have a table which contains major and minimum credit. So these two columns, because that's the closure and that's the attributes in the closure of this of major. And the other table would contain basically, so I remove this and would contain all the other attributes, ID, name, email, major, and GPA. Let's see it on the slide. So here I have major, I computed its closure, that's major and minimum credit. And then you'd have two tables. One is major, right, which contains major and minimum credit. The other one is student, which contains ID, name, email, major, and GPA. Okay? Good. Now we need to make sure that both of these tables are in BCNF. So I need to project the original functional dependencies on the new two tables and then make sure that they are in BCNF. And if they're not, I continue breaking down the tables. So let's see an example. So let's see how we do this, I mean. Okay. So we had two sets of functional dependency. ID determines all the attributes and major determines minimum credit. For the table major, the only functional dependency that is relevant is, of course, major determines minimum credit. So this is the only functional dependency that is relevant to this table. And I know that, right, if major determines minimum credit, then the closure of major is both major and minimum credit, and hence major is a super key, because it determines all attributes in this table major. And so then there is no violation of BCNF. Major on its own, this new table major, which contains the two attributes major and minimum credit, is in BCNF. Okay, what about student? So I have the student one, which contains all the attributes minus minimum credit. We have the only functional dependency that is relevant, or set of functional dependencies that is relevant, is ID determines all the attributes. Determines ID, name, email, major, minimum credit, and GPA. ID is hence a super key of the student one table. And so this implies that the table is in BCNF. So both tables are in BCNF, I'm done. Can now move on to another table in the database, check if it's in BCNF or not, and if it's not, normalize. Okay, questions? Good. Let's do another exercise. So I want you to try to do the exercise with me. If you want, do it on a piece of paper or in your head, but let's try to follow these things. Because you have a quiz on this on Moodle next. Yeah, so basically we'll give you a set of schema, relational schema, and we ask you to normalize it in BCNF and in 3NF. Okay, so let's do this example together. I have R, which has these attributes. I have this set of functional dependency, and I'm giving you the key. The key is the columns A, C. Yeah, if you compute the closure of AC to verify this, compute the closure of AC, I expect to see all the attributes in the table. If I compute the closure of AC, I get A, C, and from A I get B and E because A determines BE, and from C I get D, and hence I get all the attributes in the table, A, B, C, D. Yes, do you have questions? Somebody had the mic on, no? Okay, good. So AC determines all the attributes, then AC is indeed a key. Why is it a key and not just a super key? Because neither A alone determines all the attributes, neither C alone determines all the attributes. You can verify this by doing the projection, the closure of A and C. Is this, now the question to you is this relation in BCNF? How do I know this? I look at the functional dependencies that I have and check if A is in BCNF. So what does this mean? It means that I check every functional dependency and check if the left-hand side is a super key. Okay. So is A, I have one functional dependency, A determines BE. Is A a super key? How do I verify this? All I have to do is compute the closure of A. So what's the closure of A? It's A, B, and E. So does A determine all the attributes in the table R? No, hence it's not a super key. Okay, let's check the other. So this is a violation of BCNF because A is not a super key. This is also a violation of BCNF because if I compute the closure of C, it only gives me C and D. Okay. Hence I have two violations of BCNF. So I have to normalize the table. How do I normalize the table? I take, one table, I pick one of these, violations and create a table which contains the closure of, the attribute on the left-hand side or set of attributes on the left-hand side, and then the rest of the attributes plus the attribute on the left-hand side. So let's take the first one, right? This violation. I will create a new table, R1 or R dash, which contains A, B, and E. So that becomes my new table. Everything that depends on A. Okay? And then the other table, R2, would contain A, the attribute itself, to connect these two tables. Otherwise, you lose the connection between the tables. You remove B and E, and you have C and D. Okay. So I have now two relations, ABE and ACD. Okay. Are these two tables in BCNF? If they are, then I'm done. If they're not, then I have to normalize again. So what do you think? Are these in BCNF? How do I know this? I project the set of attributes, the set of functional dependencies on R1 and R2 and see if they don't have any violation on BCNF. So if I project F on R1, I get A determines B, right? E, or I can say A determines B from the decomposition, A determines E. Yeah. How do I know this? From the closure of A. I know the closure of A is A, B, E, and so the relevant ones is A determines B, and A determines E. Okay. So what do I know from this? What is the key of this table? If A determines B and A determines E, then A is key. Okay, because it determines all the attributes in R1 type. So A is a key, and I have these two functional dependencies. A determines B and A determines E. Neither of them is a violation of BCNF because A is a key. So I'm good to go. Okay. Now let's project these set of functional dependencies on R2. The only relevant one is, of course, C determines. Yeah, A determines B, A determines E are not part of this relation, so they'll be excluded. And then I have only C determines D type. What is the key of this table? Is C the key of this table? R2? No, because C only determines D. So really the key of this table is what? Is AC. Right? If I compute the closure of AC, yes, exactly, Gassan. If I compute the closure of AC, I get A, C, and D. Okay? So hence AC is the key. So this is a violation of BCNF. So I have to normalize this table further. Okay, so let's normalize this table further. I have R2 equal ACD, and I have a violation which is CD. I compute the closure of C, which is C and D. So I'll have a new table R3, which contains C and D. Okay, which is this, this closure of C, and then you put it in a table. And I have another table which contains the rest of the attributes plus C. Forward. So we have A and C. Okay. So now what are my tables? The final tables are R1, R3, and R4. You can verify, of course, that there are no functional dependencies now that violate the. I'll show you on the slides. Yeah. So I first decompose. Yes. So I first decomposed R into two tables: R1 A B E and R2 A C D. Okay. This is what we did, right? Exactly. And then we projected the F into ABE, and that gives me A determines BE, or A determines B alone and A determines E alone. Hence, A is the key, and hence there is no violation of BCNF. So R1 is in BCNF. And then I projected F1 to R2, and I got C determines D, which is a violation of BCNF because the key of this table is AC. Okay, so I decomposed it further into two tables, C, D, and A, C. And that's how I'm done. Questions? Now I can check, right, whether R21 is in BCNF. Of course, it is in BCNF because C determines D, and hence C is the key of this table. And for the final one, right, there are no relevant functional dependencies. There's nothing that says A determines C or C determines A. Hence, the key is AC. And I don't have any violations of BCNF. So R22 is also in BCNF, and so I'm done. Questions? Okay. So you have two options. We're way ahead of time. So we can continue the second half of the lecture now, or we can, stop here and then talk on Tuesday. So give you some time to, digest this. I prefer this option, that you digest this, review it, and then we talk on Tuesday, continue with the lecture, because we're way ahead of time right now. You have 2 minutes, less than 2 minutes to decide. Give me some thoughts. Should we continue, or we should stop here and continue on Tuesday? Okay. Okay, so let's do that. Let's stop here. Okay, so, and digest it, go through it, and then on Tuesday we continue. Okay, so we're gonna do 3NF on Tuesday, and then you'd have enough time to basically still do the quiz. The quiz is the end of the month, right? End of the month. How many lectures we have left? So after that, you have no SQL, which you will do online on your own. It's very straightforward. It's nothing complicated at all, and you have a quiz on it on multiple choice quiz, and that's it. So we have like maybe one lecture, and then you have another lecture on your own. Okay? Yeah. I'll talk to you guys on Tuesday. Bye.